theoretical concept of hybridization. It is just mixing of two or more things. If you talk about s orbital is spherical and p orbital is dumbbell. S orbital is spherical and p orbital is dumbbell, right? Plus minus, there is only plus. So s orbital and this is p orbital. When they mix, they form orbital like this, in which one lobe is bigger than the other. Say in this case both the lobes are equal, but when s orbital mix with p, then the number of orbitals which mix together is equal to number of hybrid orbitals. Okay, when they mix, they give new orbitals, or these two new orbitals are like this. Means they have bigger one lobe and smaller the one is smaller lobe and other is bigger lobe. So if bigger lobe overlap, the area of overlap is more, so strength is more. That means hybridization takes place to strengthen the bond, right? So now let us see what is its definition. So if question is define hybridization, so you can say it is just mixing. So write down the exact definition. The phenomenon, you can write from here, the phenomenon of mixing of atomic orbitals, phenomenon of mixing of atomic orbitals of same atom. Is it visible? With slight difference in energies. Say energy difference should not be very large. Mixing of atomic orbitals of the same atom, first thing. Second thing, there is no large difference in energies. Means those belongs to the same shell. Orbital like 1s orbital cannot mix with the 2s. Okay, but 2s and 2p they can mix together. 3s and 3p they can mix together. Okay, means they should have slightly different energies. Okay, so of slightly different energies, so as to redistribute their energies, so as redistribute their energies. Like s orbital is lesser in energy, more stable. P orbital slightly large in energy. So when they mix together, what happened? Energy of p orbital is slightly decreased, energy of s orbital is slightly increased. So midway there is a mixing, means hybrid is formed, and give new orbitals of equivalent energies and shape. And these new orbitals are called hybrid orbitals. These orbitals are called hybrid orbitals, and they are lying in specified directions. For example, if we have, just like now we can apply Vesper theory. If we have two hybrid orbitals, so tell me what is the arrangement of those two hybrid orbitals? It is linear. When two hybrid orbitals are there, they lie in a straight line. So now conditions for hybridization. Conditions for hybridization. First, define hybridization, that we have covered. Now, what are the conditions for hybridization? First condition, only the orbitals of the same atom are taking part in hybridization. Okay? The first condition is only the orbitals belonging to the same atom are taking part in hybridization. This is the first condition. Now, from the definition, tell me what should be the second condition? The orbitals taking part in hybridization, I can write this only, should have same energy or should have small energy difference. Okay, this is the second condition that can be taken from the definition. Now, third condition. Say, after getting these conditions, say, if we have methane or ammonia, to write third condition, I am giving you example. Say, in carbon in ground state has 2s2 and 2p2. Tell me, how many electrons are required to form CH4? In methane, how many unpaired electrons are required? That's it, 4. But in ground state, GS is ground state, stable state of carbon atom. In stable state of carbon atom, how many electrons are unpaired? Only 2. That means to form methane, carbon should be in excited state. One of the electron from 2s should shift to 2p. Right? After the shifting, now it has 4 unpaired electrons and now it undergoes hybridization. That means electron is promoted to 2p and then it gets hybridization. 1s and 3p. So sp3 hybridization. 4 hybrid orbitals are formed. In ammonia, nitrogen has 2s2, 2p3. So now tell me, in ammonia, in nitrogen in ground state has how many unpaired electrons? 3. So, see, only 3 bonds it has to form. and nitrogen has 3 unpaired electrons. So there is no need to promote this pair. That means lone pair can also participate in hybridization. Okay, so promotion of electrons, here promotion is essential, but here promotion is not required. So third point is promotion of electron is not essential. Promotion of electron is not essential prior to hybridization. In methane, you can see that we need 4 unpaired electrons, but carbon in its ground state has only 2 unpaired electrons. So promotion is required. Excitation of 2s. Promotion means excitation. Okay. So 2s electrons should be promoted to 2p in order to get 4 unpaired electrons, so that they can overlap with 1s orbital of hydrogen to form methane. But in this case, nitrogen has 3 unpaired electrons. Nitrogen has 3 unpaired electrons, right? So when it has 3 unpaired electrons and only 3 bond it has to form, then there is no need to promote the electron. There is no need to shift this electron to anywhere. Just these 3 can. That means there are 4 hybrid orbitals. Out of 4, 3 are form bonds, bond pairs, and 1 is lone pair. Not only half-filled orbitals. This is the example. Even fully filled orbitals can participate in hybridization. See, you can change the wording you can change, but don't change the meaning. If you shuffle these words, okay, you can write half-filled as well as fully filled orbitals can participate in hybridization. That is the same thing. If you write half-filled as well as fully filled orbital can participate in hybridization, it has same meaning. Or not only half-filled, even fully filled orbitals can participate in hybridization. Or not only half-filled, but fully filled orbitals can participate in hybridization. But please don't change the meaning. Okay? That's it. Okay, so these are the conditions of hybridization. That orbitals belong to the same atom. Orbitals taking part in hybridization should have same energy. Promotion is not essential. Okay, and half-filled as well as fully filled orbitals can participate in hybridization. Now, characteristics of hybridization, or we can say features, salient features of hybridization. Visible? Yes. So first is same conditions and definition. You can combine those statements, you get the features. First, only orbitals of slightly different energies. Can participate in hybridization. Yes, like in carbon, it has 1s2, 2s2, 2p2, right? So carbon, if you write, it is 1s1, 2s2 and 2p2, and after promotion it is like this. So it means that this 1s will not participate in hybridization. 1s cannot mix with 2p. 2s can mix with 2p because they have slightly different energies. Because see, 1s, 2s, 2p. It is like this. So 2s and 2p, they have slightly different energies, so they can participate, they can mix. But 1s cannot mix with 2s and 2p. Now second thing, if you think that, say, if we have nitrogen has 2s2 and 2p3. So in this case only 3 bonds we have to form. So why not these 3 can mix? But hybridization tells us that orbitals of the same shell cannot hybridize on its own. They cannot mix together. They can mix with s. There should be some other subshell. Okay, so 2px, 2py and 2pz mix with 2s. Got it? Means we can write it like that: orbitals of a particular subshell. Orbitals of a particular subshell cannot hybridize of their own. Because they have same energy. See, their shape is same, dumbbell, all are dumbbell. Their energy is same. So they cannot mix together. Okay, they can mix with any other orbital having, which is in the different subshell of slightly different energy. Point is the number of hybrid orbitals, is equal to number of atomic orbitals participating in hybridization. Participating in hybridization. Third point, simple. If one S and one P they mix together, then we will get two sp hybrid orbitals. See, one S and one P. When they mix together, I will write 1s plus 1p orbital. They mix together, we get two sp hybrid orbitals, right? 1s plus 2p. They mix together. Then we, how many, or we get 3 sp2 hybrid orbitals. Now tell me, if 1s and 3p orbitals mix together, tell me what would we get? If 1s and 1p mix together, we get sp hybrid orbitals. How many? 2. Because there is 1s and 1p. If 1s and 2p combine together, then we get 3 sp2. Very good, Raghav. If we combine 1s and 3p, then we get 4 sp3 hybrid orbitals. It means it has 1 part of s and 3 part of p in each orbital. 1 part of s, 2 part of p in each orbital. 1 part of s, 1 part of p in each orbital. Hybridization never takes place in an isolated atom. Means if atom is isolated means when it is not forming bond, simple atom is there, then hybridization has no role to play. There is no hybridization of an isolated atom. But and it occurs in atoms taking participation in bond formation. Those which can form bond, okay, that only undergoes hybridization. Actually, main advantage is I showed you that if we have P and S, they overlap to form 2 hybrid orbitals having large size. So when they have large size, they can form stronger bond, means overlapping region is more. So hybridized orbitals are most effective. Hybridized orbitals, or we can say hybrid orbitals, are more effective. Hybrid orbitals are more effective in forming stable bonds than pure atomic orbitals. That's why we use the concept of hybridization, because hybrid orbitals can form stronger bond. They can form more stable bond than the pure atomic orbitals because their area of overlap is large. Effectiveness of overlapping is more in hybrid orbitals rather than pure atomic orbitals. So this is the point number 5. Now, see, if you talk about shape, if we have sp hybridization, arrangement is linear. If we have sp2 hybridization, arrangement is trigonal planar. If we have sp3 hybridization, arrangement is tetrahedral, and so is the shape. Okay, so the shape of the molecule or shape of the covalent molecules can be predicted on the basis of hybridization. the shape of covalent compounds can be determined or can be predicted on the basis of type of hybridization. So we know the type of hybridization of the central atom, we can predict its shape, arrangement or geometry. So these are the features of hybridization. We have done definition of hybridization, conditions for hybridization, as well as features of hybridization. Okay, now first case, let us discuss sp hybridization. So in sp hybridization, we have one s and one p orbital. Okay, when they mix, that is called sp hybridization. We get two sp hybrid orbitals and they are arranged in linear arrangement. There is linear arrangement of these two hybrid orbitals. Only bigger lobe participate in overlapping. Smaller lobe will not take part in bonding. Keep in mind this thing. Only bigger lobe participate. So arrangement is linear. And hybrid orbital has either lone pair or they form sigma bond, but unhybridized orbital can form pi bond. Okay, so now for example, for in sp hybridization, let us discuss the case of ethine. So see, in ethine, it is C2H2, or you have drawn its structure like this. Am I right? So see, tell me, each carbon has how many sigma bond and how many pi bonds? When this is like when plus overlap with plus, then negative overlap is negative. So we get larger part of plus and larger part of negative. Okay, but when we have larger part of positive and positive part interact with negative part, what happened? We have smaller positive and smaller negative. So say when we have S, it is positive, in P positive negative. So when positive interact, it becomes bigger. When positive, this plus interact with negative, this is destructive interference, so it becomes smaller. Each carbon, say this is sigma and pi, means each carbon has 2 sigma bonds and 2 pi bonds. 2 sigma, 2 pi, each carbon has 2 sigma bonds and 2 pi bonds. Now got it? Why positive part is bigger and negative part is smaller? Okay, this is related to wave concept. Okay, now let us discuss about structure of methane. So ethine. Ethine is also called acetylene. Its another name is acetylene. Okay, now carbon, but each carbon form 4 bonds, so it should have 4 unpaired electrons. First condition. Out of 4, only 2 form sigma bonds, so 2 hybrid orbitals and 2 unhybrid orbitals. See, carbon in its ground state, its electronic configuration is 2s2 and 2p2. So in excited state, one of the electron gets promoted from 2s to 2p. Okay, 2s to 2p. So now we have 4 unpaired electrons, but out of 4, only 2 gets hybridized. Why is it so? Because it forms 2 sigma bonds only. Each carbon forms 2 sigma bonds. That means this carbon has 2 smaller part. I am not showing. There is no need to show smaller part because that is not taking part in hybridization. That we have shown earlier to just show you how it responds when they mix. Positive part becomes bigger, negative part becomes smaller. So negative part I am not showing. Only the part which is participating in bonding, that is shown here. Each carbon has 2 sp hybrid orbital. This is sp hybrid. This is also sp hybrid. And along with this, there are 2 unhybridized p orbital. So 1 and 2. There are 2 unhybridized p orbital. Okay? Plus, minus, plus, minus. It's your choice to write plus minus or not. It is up to you only. Now, second carbon. In second carbon, 1 sp hybrid orbital overlap with each other. They should be equal in size, okay? And another sp hybrid orbital. And 2 unhybridized p orbital. This plus minus, it is your choice. Better to avoid the confusion, better to remove them. There is no need to write plus minus, okay? And plus minus, you know what is that? Crest and trough. So now, say 1 sp hybrid orbital of each carbon overlap with each other to form carbon-carbon sigma bond, and 1 carbon left, sp hybridized carbon left on each carbon overlap with 1s orbital of hydrogen. It overlap with 1s orbital of hydrogen. 1s orbital of hydrogen. That's it. This is CH sigma bond, CH sigma bond. Concept of sigma bond is clear. This hybrid part shows crest. You know, 1s has crest plus part. Okay, so this plus part overlap with plus part. See, 1s orbital, its shape is like this. That you know. Only plus part is there. Okay, so crest, 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 crest. Trough part is not participating. Pi bond. This orbital has same symmetry as this. Orbitals of same symmetry overlap sideways. Okay, to form pi bond. Right? This is 1 pi bond. 1 electron cloud above the plane, other electron cloud below the plane. Okay, and second p orbital on each carbon having same symmetry overlap again sideways to form second pi bond. But now say two electron clouds, one above the plane, other below the plane. So what about other two? Second pi bond is formed. Again we have two electron clouds, total 4 electron clouds. So how we will arrange them? One above the plane, one below the plane. Okay. So what about other two? Front and back. Front and back. Because on this side there is carbon hydrogen sigma bond. Okay. So it is like this. One above the plane, one below the plane, and others are like this. Okay. So they form a whole cylindrical shape. They form a cylindrical pi electron cloud. Like this. See. So it is like carbon, hydrogen sigma bond, carbon, hydrogen, carbon, carbon sigma bond, and one electron cloud above the plane, other electron cloud below the plane. So they are like this. That is cylindrical pi electron cloud. There is a formation of cylindrical pi electron cloud. The shape is linear, right? How do we write this pi electron cloud? Because there are 4 electron clouds for 2 pi bonds. One pi bond has 2 electron clouds, one above the plane, one below the plane. Okay. So in ethine there are 4 electron clouds. Okay. So now sp2. In sp2, we have carbon, S and 2 P. So 3 orbitals overlap. sp2 hybridization, and we get 3 sp2 hybrid orbitals, and arrangement is like this: trigonal, planar. Arrangement is trigonal, planar. 1s and 2p, they mix together and we get trigonal planar arrangement of 3 sp2 hybrid orbitals. They are all sp2 hybrid orbitals. Done. So let us discuss the case of ethene. So in ethene, it is C2H4. So in C2H4, you know that it is like CH2 double bond CH2, or we can write it as C double bond C H H H H. That you have done in class 10. Okay. Now, again tell me now, each carbon form how many sigma bonds and how many pi bonds? There are 3 sigma bonds and 1 pi bond. Again 3 sigma bond, 1 pi bond. So, carbon in ground state again has 2s2 and 2p2, but it forms 4 bonds. So it goes in excited state. 1. So 4 unpaired electrons. Out of 4, 3 are involved in sigma bond formation. So sp2 hybridization. So each carbon has sp2 hybridization. sp2, sp2, sp2. One sp2 hybrid orbital overlap with each other. and other 2 on each carbon overlap with 1s orbital of hydrogen. Right? And each carbon left with one unhybridized orbital. And that unhybridized orbital, these are unhybridized orbital. Okay? They overlap sideways. So they form sigma bonds. And electron cloud is formed one above the plane and other below the plane. One above the plane, one below the plane. And arrangement is, or shape is, trigonal. Okay. So now sp3 hybridization. In sp3 hybridization, okay, Siddharth, Poonam means Siddharth, right? Okay, Siddharth. In sp3 hybridization, one s and 3 p orbitals. You can write plus minus like this or either way. And so when these 4 orbitals mix together, it undergoes sp3 hybridization, form 4 sp3 hybrid orbitals, and they are arranged like this. They are sp3 hybrid orbitals, means plus 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 plus, right? Minus 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 minus. Arrangement is tetrahedral and angle is 109 degree 28 minutes. Yes, we have not discussed about angle. So in sp, linearly arranged, so 180 degree angle. In trigonal planar, there is 120 degree angle, and here angle is 109 degree 28 minutes. So we will discuss the angle in detail in the next class. Okay. Now just we should look at the shapes only. See, let us take example of methane and ethane, both. In methane, see, it is CH4 and this is C2H6, means CH3 CH3, or you can write it as like this. So each carbon form 4 sigma bonds. In methane, each carbon form 4 sigma bonds. That means carbon in the ground state, again same condition, there are only 2 unpaired electrons, so it undergoes excitation and we get 4 unpaired electrons. All are hybridized because it forms 4 sigma bonds. Now carbon sp3 hybrid orbital, and each sp3 hybrid orbital overlap with 1s orbital of hydrogen. So tetrahedral arrangement like this. In ethane, each carbon has 4 sp3 hybrid orbital. Arrangement is tetrahedral. Out of 4, 1 of each carbon overlap with each other to form carbon-carbon sigma bond, and one s orbital of hydrogen. So it is like this. You know, angle is 109 degree 28 minute, and carbon hydrogen bond length, carbon sp3 hybrid, carbon hydrogen bond length is 111 picometer, keep in mind, and carbon carbon bond length is 154 picometer. Carbon carbon single bond length, carbon carbon single bond length is 154 picometer. Okay, in ethene, okay, let us write all the three and compare. This is ethane, this is ethene, and this one is ethine. Ethane, ethene, and ethine. If we talk about bond angle, here bond angle is 109 degree 28 minute, here angle is 120 degree, and here angle is 180 degree. Now tell me, say there are two angles, HCH. According to hybridization, that is sp3, angle is 109 degree 28 minute. In ethane, each carbon is sp2 hybridized, so bond angle should be 120. In ethine, each carbon is sp hybridized, so bond angle should be 180. But now tell me, HCH and HCC, are they equal or different? HCH, this one, theta 1, okay, and this one, theta 2. So tell me, are these theta 1 and theta 2 is equal or different? It is different. Why is it so? Because you know, double bond repel more than single bond. Double, because this is bulkier group, so it should be away from hydrogens. Hydrogen, they are very small, so they can come closer easily. And at the same time, single bonds repel less than double bond. Yes, it is unequal. So which one is larger? Obviously theta 2 is greater than theta 1. Okay, there is slight difference. It is 121 degree, it is 117.5 degree. Okay, because of this double bond, single bond, size, all that counts. Okay, now tell me, carbon sp3, carbon, it is 154 picometer, carbon single bond. Okay, and what about carbon double bond? It is 134 picometer, and carbon triple bond length, okay, bond length, that is 120 154, 134, and around about 1, this is 120 ethine. Yes, it is 120 picometer. Now, carbon hydrogen bond length of sp3, carbon hydrogen bond length of sp2, and carbon hydrogen bond length of sp. You know, sp3, sp2, sp, which one is larger in size? sp3, because that has more number of orbitals involved. Okay, 1s3p, so that is bigger in size. 1s2p, smaller. 1s1p, still smaller. Okay, yes, Namita. So sp3, that's why its bond length is 111 picometer. Here it is 110 picometer, and it is only 108 picometer. Though all are single bonds, but hybridization plays an important role. If we talk about reactivity, you know, because of pi bond, it is more reactive. In triple bond, pi bond is delocalized. It is not locked. This pi bond is locked above and below, but this pi bond is delocalized. So alkene is more reactive because of pi bond. Though alkyne is also reactive, but less reactive than this. In the chemical properties hydrocarbon chapter, we will discuss all the reactivity concept. Ethane, because single bond, sigma bond, very strong bond, so it is least reactive. Okay, so this is all about today's lecture.